Okay, so we're continuing with localization. Two, three, three. Okay. Oh, that's the eraser. That's kind of big. Okay, so let's do localization. More of this. So continued. Okay, so let me just recall what we did. So last time, so we defined, so given S subset of R, which is multiplicatively closed. Okay, and then I said S doesn't need to be, well, okay, so let me just do this. Given S subset, so we defined the localization. LS from R to S inverse of R, the localization map. So the localization map. And kind of the important defining property. So we had this for rings. So there's this one. So we also have a version for rings, or we also have a version for modules. For R modules. So LS from M to S inverse of M. And so these were these S inverse things were things where you allowed denominators in S. Okay, and the important part was that M1. So the important property was that M1 over S1 was equal to M2 over S2, and this applies in both if and only if there exists some S3 and S3 such that, well, S3 times the cross product, or whatever you call this thing, S2 M1 minus S1 M2, this thing was 0. Okay. All right. So this is the definition that we had, and they were just kind of like fractions with denominators in S. A quick comment here is that, so last time here I said, we took 0 not an element of S, but we could, if you want to do 0 an element of S, 0 an element of S, then define S inverse of M to be equal to 0, right? For all M. Okay, or you can try and get this property from the definition. Essentially, if you allow 0, then you essentially kill everything by this little property here. Okay, so Jeremy wanted to talk about the geometry of this a little bit more. I did some doodles. So let me say a little bit more about the geometry. So let's do an example. So let's let R be C of XY, our favorite ring, and P be this ideal here. So this is the maximal ideal corresponding to the point 0, 0. in C2. Okay. So then what we did is we defined, so there was this weird notation where we did R of P, right? And so this was, S inverse of R, where this S was R set minus P. So if you remove a prime ideal, this is actually a multiplicatively closed set. So that's something that you should check. Okay. So what does this thing look like? Okay, so this is, so this thing here, so R of P. Okay, so this thing looks like, so this is, so sometimes we write this like this, C of X, Y like this. Okay, so this is P, that's R. Okay, so this is the set of F over G, right? So F of XY over G of XY, right? Such that, well, G of 0, 0 is not equal to 0. Does that make sense? So like, so remember that an element is only in this ideal if G of 0, if only its evaluation at 0 is 0. Okay, so what this does is these are all functions. So these things here, these are all the functions where, rational functions, where evaluation at 0, 0 makes sense. Okay, so this is kind of like functions which make sense locally around this place P. Okay, so all right. So what does this thing look like? Okay, so I said that this is a neighborhood around. So the idea was that here, right? So this is A2, which is spec of C of XY. So A2 defined over C, say, right? So then we have the point, this is the point that corresponds to the prime ideal, so that's 0, 0. And then this thing here, the spec of C of XY, XY here. So this thing is kind of like a neighborhood here. Okay, and actually, so this is like, okay, so this thing we'll see in a second. This corresponds to the topological space of this. This corresponds to all prime ideals contained in XY. So prime ideals here, they could be, so prime ideals okay. So again, we draw usually the closed points, the complex points. So those only correspond to the maximal ideals. But there's other ideals too, right? So you could have a subvariety like this, right? And a subvariety like this, right? So these could be prime ideals I'm drawing here. So really, this thing here is kind of like all the things that are all of the subvarieties here that specialize to this point. In particular, everything that passes through here, that point. That's what it looks like. So remember, there's points of this. There's points of here. There's non-closed points of this. I.e. points that don't correspond to elements of C2, right? The things that are not maximal ideals. Correspond to irreducible subvarieties. Okay, so this is kind of the cartoon picture here, is that this thing here will be a subspace in this topological space. And it's kind of like all the things that sit inside the maximal ideal XY. So we think of this space here as kind of a neighborhood of 0, 0. Okay. Another thing that is maybe encouraging here is that so we haven't really said this at all, but so a spoiler is that that this thing here. So this is a local ring, right? It has a unique maximal ideal. And the maximal ideal is, well, we can call it xy, c of xy here. Well, the thing's vanishing at 0, 0. And we can call this, maybe we can call this M. And it turns out that the inverse limit, we saw this before, of c of xy modulo m to the n. So this thing is isomorphic to c of xy. So kind of the completion of this thing with respect to the maximal ideal is the power series ring. So you should think of this thing as, so actually, you know, sorry, let's do this. I mean, xy. I mean, what I wrote that was still true, but this is what I wanted to say, is that if you complete the local ring, you get the power series ring. So in power series should be thought of as kind of like higher order information. Actually, we have something that's even cooler. It's that c of xy intersect the rational functions. This is this ring. So they're like power series. So this thing, so another way to view this is that this thing is like power series in xy that are finite, have finitely many terms. Maybe you guys are doing power series and Laurent series in complex analysis right now. But this is these are like the finite, you know, expansions in x and y. Oh, I guess no, sorry. That's not correct. They don't have finitely many terms. They're power series in x, y that are algebraic functions, I guess. Sorry, that are rational functions. That was incorrect. Right. This 1 over 1 minus x is in there, and this has infinitely many terms. Right. Right. Okay. So maybe this helps you think about this, but they're essentially like the things in the fraction field that have a power series expansion. Okay. So yeah, so that's one way to think about this one. The other example, any questions about this example? Maybe I can highlight the unproved assertions. Would that be helpful?
Yes.
Yeah.
Okay. So so what can't we prove yet?
I'm also a little confused about, like, I don't know if I'm reading too much into this picture. Is the implication that this is a topological space, right? We're defining
this
it.
It's a topological space, but it's more than that. It's a scheme, and it has a sheaf of rings, right? So yeah, it's a topological space, but it has additional structure to it. If we were just going to consider a topological space, then you know, the reduced version of the ring will give the same underlying topological space. So not only, yeah, yes. So it's a topological space.
Okay, and so these points are prime ideals. And are you also claiming that this is like we can impose a metric on this? Is that what these open?
Well, it's like a wannabe metric. You know, it's like we don't really have a metric, right? And so it kind of is like a metric, but instead of using a metric, well, we're doing something completely different. We're using vanishing of ideals, things like that. So this is like, you know, a replacement for metrics.
Okay.
So the idea is to kind of like transfer our intuition with metric spaces and stuff to ring theory. If that makes sense.
Okay, I'll think about it a little more.
Yeah. Okay, so this is something I need to prove. This is a need to prove. This statement, right? This statement that so the prime ideals in here are the prime ideals here. So that means it's a unique maximal ideal. So this is a need to prove here. And then this is a need to prove. This statement here. But I just kind of want to, this is kind of, I just wanted to tell you what's maybe, I don't know how to think about it, but there's a relationship between these things and power series rings, and power series rings are like, we've already talked about them as being kind of local information, like better than the tangent space. Okay. All right. Any more questions? Feel free to shout out questions. Okay. So the other example we gave was that if we took this thing, if we took this thing to be R, and then we took, then we localize. So this thing, so what is this thing? So this thing is this, the two axes, right? So this is the axis where y is equal to 0. This is where x is equal to 0. Okay, and the idea behind, okay, so we have this, and then the kind of general picture that I drew was that if so, the localizations are f for f and r uh, are like are removing slices from spec R. Okay, so anytime you kind of like allow denominators, you're going to be removing stuff. Okay, so you know, you don't want your denominator to be 0. Okay, so RF, as I want to remind you, RF is R1 over F, right? And this is, you know, S inverse R, where S is the multiplicative set, 1 F, F squared, F cubed, blah, blah, blah. Okay, so when we do this, the idea is that you have, here's spec R. I'm just drawing it as a box. And then you have this slice in here, which is the place where F vanishes, V of F. Okay, and then what's left over, right? This negative space here, that's what we should think of as spec of R of F. And you can actually make this precise, right? And this will come up in a lemma that you know. So maybe I can say the lemma over here that we use for both of these. So the map. So let's say let L S from R to S inverse of R be the localization map. Then the set of LS inverse of Q for Q in spec of S inverse of R. So this is the localization here. So this is equal to the set of prime ideals in spec of R such that P intersect S is the empty set. So the prime ideals of the localization are really the prime ideals of spec of R that don't intersect the multiplicative set. Okay, this is what I'm using to draw. So this is what we use to, this is kind of what we use to draw the pictures. Okay. So the prime ideals that avoid this multiplicatively closed set. In an exercise before, this VF piece here, right? So VF was, so this is equal to, this can be identified with spec of R mod F. And this is a closed subspace. And then later in life, you learn that it's a closed subscheme. Right? So this thing, so whenever you take a quotient, it's like a closed thing, right? So in particular, like, yeah, so these quotient rings are correspond to closed closed subschemes. And so what we're removing here is we're removing this closed subscheme, right? So this thing is an open. This part here is, so this thing is closed, and this thing here is open. Okay, this is what's called a principal open set. All right, and so let's go back to this example. So this is about removing a slice. Let's go back to this example here. So in the example last time, let's look at, let's localize at X bar in this ring R. Okay, so X bar, so where X bar is equal to 0. Okay, so what I drew this in pink. So here F is, this is what corresponds to X bar. So this is where X bar is equal to 0. So that's this piece here. This is where X bar, this is V of X bar in the picture above. Okay, so if I take this whole thing and I'm just removing this, what we're going to be left with is what we're left with. Is the following. Like a hole there. Okay, and so let's check. So let me just kind of prove a little thing for you. So this is what we're claiming. This is okay. Does this kind of picture make sense? So this should be spec of, or let's see, when you did it in purple. Okay, we'll do it in purple. This should be spec of C of xy mod xy localized at X bar. Okay, so that's what this thing should look like. It should just look like, I guess, the x-axis with, so the guess is that it just looks like the x-axis, right, with x removed. So the guess, so from the picture, we guess that that this thing. Okay, so here's a good question, right? So what is this thing? I shouldn't have. I wish I could cover. If I were at the board, I would have used my hand to cover this. But what do you think this thing looks like? So if I take, so what is if I had this closed line here, what would that be? What ring would that be? Is it okay if I call on you, Jeremy?
I'm still struggling a little bit with these pictures.
Yeah. So like this line, this picture here, what is this picture?
C of xy or no?
That would just be C of x, right? This one here, the two-dimensional one, right? That's C of xy, right?
That's all filled in, right? For C of
Yeah,
X.
this is all filled in.
Okay.
Okay, yeah, exactly.
Okay.
Right?
So
And so if I wanted to remove a point here, right? So suppose I remove the origin, right? What would that look like? So what's the origin in terms of slices? So like, let's go back to this picture.
So
So the origin is 0, 0?
Yeah, the origin is 0, 0, but in just the real line, we only have one. So this only has one coordinate. So this is like the x-axis. And then this thing here is the xy plane. Right? So the origin is exactly where, so this point in here, right? So if I just do this point corresponds to, well, C of xy mod x, or this thing corresponds to the maximal ideal x in C of x. Okay? So it's a maximal ideal because the quotient is a field. All right? So if I wanted to remove this point, I could just localize at x. Do you guys agree?
Yes.
So that would be, so we expect this picture here to be this 1 over x. Okay? But I didn't do any computations yet, right? All I did was doodle.
So,
Right.
Taylor,
I did this computation without even doing any algebra. Yeah.
so these places where we have, I think I'm was, or maybe I'm even further behind than Jeremy. So we have C of xy, we're modding out by xy. That's like our first picture. So that might,
Yeah.
I was failing myself because I was like, I didn't really understand what was going on there. I didn't know if we were taking the plane and removing like
Yeah. So let's do that. Let's do that. So C of xy. So this is A2. And this is spec of C of xy. Okay, so this is A2 with coefficients in C. Okay, and then we have a subspace, which is this here and here. Right? This subspace is V of xy. That's what I'm starting with.
And just for clarity, V of xy is just, it's all prime ideals containing.
Yeah, so it's prime ideals containing xy.
Okay.
Yeah. So this is the set of P, right, in spec of C of xy, such that xy is contained in P.
Okay.
So what this means, contained in P, it means that like mod P, this thing's going to be 0. And when you go mod P, that's like evaluation at a point. So whenever you reduce something mod P, you should think of that as like evaluation. This is one way to view this thing, right? That this is as a closed, so this side here, this is as a closed, as it sits inside A2. Okay? The other perspective, right, is that this thing here is also spec of C of xy mod xy. that's kind of the interesting part, is that there's this correspondence, is that this thing also corresponds to this quotient ring. So not only is it this sub thing, it's this quotient ring here. So closed subschemes correspond to quotients of rings. Closed subspaces are quotients. And kind of open subspaces are localizations.
Sorry, can you say that one more time?
So closed subspaces, right? Those are quotient rings. So in the dictionary, to get a closed subscheme, you take a quotient of a ring, right? And that's how you get these V's. To get an open subspace, or a principal open subspace, you do the purple. You take the complement and you do the localization. Okay. So this thing has two lives, right? So this thing is so we haven't proved all that yet, but that's the way I'm telling you, that's how it works. Okay. So we have this thing, this is closed inside here, and now I'm just dealing with this. Okay, so now I'm just dealing with it by itself on this screen here. Okay. Then to localize, well, I'm going to localize at x bar. So what I'm going to do is I'm going to remove this line here, right? And so I only want to consider the purple. Well, I mean, the purple is not all this, right? The purple is actually just this and this, right? Because we're only working on these axes, and so we're left with this thing with the origin removed. And because we know how to draw this, so this is just an x coordinate. This is the x-axis, and we're removing a point here, right? So like this thing corresponds to, you know, this thing corresponds to this x, you know, just this single slice. Then we can just remove that by localizing. Does that make sense? Let's check to make sure that I was correct, though. Okay. Okay, so one of the theorems is that we want, so there's a theorem. And this works for rings and modules. Or a lemma, I don't know what you want, let's just call it a theorem, whatever. So let M be an R module. And let S, a subset of R, be a multiplicatively closed set. Then the kernel of this map, the localization map, from M to S inverse of M, is you know, the set of M and M such that there exists some S in S with S of M is equal to 0. So they're the things killed by S. All right. All right. And so the proof is you just apply that definition, right? So LS of M, this is M over 1, right? And M over 1 is equivalent to 0 over 1 if and only if there exists some S and S with S times 1M minus 1 times 0 is equal to 0. And that's equivalent to there exists some S and S with SM equal to 0. Okay, so that's what tells us what the kernel of this thing is. Okay, this works for rings, it works for modules, because ring maps are also module maps. Okay, and so so let's go back to this thing. So let's go back to this example here. So the kernel, so let's look at L X bar. So this is the localization that, so I'm giving this a slightly different name. So we have C of xy mod xy. So this goes to C of xy mod xy localized at x bar. Okay, so the kernel of this thing is equal to the set of f in this thing such that there exists some n in the natural numbers where x bar to the n is equal to x bar to the n times f is equal to 0. Agreed? That's what, this is the multiplicative set. Okay, so clearly here, so we have that y bar is an element of this thing. Right? So that means that y bar needs to go to 0. Okay, and so what I did is I took this ring here, and what happens when y bar goes to 0? Right, so when y goes to 0, that kills this thing, and that kills this thing. Right, it actually kills this whole relation here. Right, so this relation gets killed. Okay, so this thing, so it's C of x. Well, there's no denominator anymore. Right, because the denominator went to 0. It's a multiple of, so like, notice that, you know, that's 0. I mean, it was 0 before, but yeah, anyway. Lx is not equal to 0. So this thing is just this. I mean, you could write it like this, but there's no bar anymore. It doesn't matter because it's a free, you know, there's no relations on it. Or sorry, not parentheses x. Parentheses x would mean the ideal. That's kind of a tricky point. Right, so this is C of x, 1 over x. Yeah, so just kind of a fair warning. It's just a notation thing. C of x. So this one's equal to, this is the set of, well, we wrote this one. And then this one is the set of f of x over g of x, where g of 0 is not equal to 0. So it's like the opposite, right? So here we're allowed g of 0 is equal to 0. So in the picture here, like this side is, so this thing is like, okay, so let's do blue and then we'll do green. Or let's do it the other way. So, well, yeah, let's do blue and green. Okay, so this part here. Here's the line. This is the x-axis. The blue part is so the blue part is okay. So we draw it like this. So it's like kind of like a neighborhood like around the origin. And then the green part is everything but this thing removed. So it's this. So it's this. Right. All right. Okay.
I have a question. So
Yeah.
I understand. So I'm understanding the green part and the fact that we have a whole, I guess what we're calling the origin here. I'm not really understanding the blue part. Like, why is it everything around? I know that you've talked about this a little bit, but I'm still not understanding. Why is it everything close to?
So the idea is that this is like, okay, so this is like power series. In X. And so if you truncate a power series, right? That's if you truncate a power series to order 2, that's the tangent space. Right?
Sure, but how are we how are you saying that this is a power series?
How do you see that this is a power series? Okay.
Like, where are we getting that information then?
How do you see that this, so how is f of x over g of x? So why does this have a power series expansion? So this is a holomorphic at 0, not meromorphic. Agreed?
Taylor, is that holomorphic?
Holomorphic, yeah, holomorphic.
Never heard that word in my entire life.
Analytic?
I know that one, I think.
So it has a power series expansion. This thing looks like Cj x to the j. J is equal to 0 up to infinity for some Cj's. It has a power series. And so if you were to truncate the power series, right, then you would get a tangent space. And so this is kind of like some higher order tangent space.
Okay, like I can agree with that, but I'm okay. I guess I
I
have
would
to
say if you do the doodles, just I think I felt the same way. Like when I first saw this, like I was like, what the hell? If you do the doodles like this, it'll help you.
Okay. I guess I'll believe you.
I mean, how did I get from this crazy idea? So by the way, this is a growth and deque thing. Okay. So so how did we get from this crazy idea that this ring is supposed to be like this, right? Like I don't know. Growth and deque came up with this. It's a great idea. It works, right? It allows you to compute things really quickly. Like I don't know. I think it was Growth and Deque who realized this. Yeah. But I mean, all I've done is I've showed you that this is this is a subset of the power series ring. That's what I've explained before.
So
These
like
are great questions, by the way. I think this is super important. Like, if you can see the pictures and you can see how to draw things, right? Then things become a lot easier. Like commutative algebra without these doodles is really hard.
is my mic working? Can you hear me?
Yeah, I can hear you.
So like usually when I see like power series and a circle, I think of like, I don't know, like a radius of convergence. Is that
Exactly.
at all what this is? Kind of like that?
Kind of, right? It's kind of like that, but the whole thing is like we don't really care about convergence anymore.
What's happening inside this circle that's not happening outside? If this is like a local
Yeah. Okay, so that's a good question. That's actually a really good question. So like, what is it that makes it a circle inside the circle that's not above the circle? So this is what I said before, that so if we take this, where's this theorem here? Here, let's look at this. So this is the set of prime. Okay. So what is this saying? This is saying this is the statement that I made before here, that this is saying that for in the case of S is R set minus P, well, then let's look at this. So Q, so for Q intersect S is equal to Q intersect. So here I'm taking Q in spec R. Okay, so I'm explaining to you why this is like local. Like what's so local about this? All right. So what does this have to do with P, right? The place P. So this is Q intersect R set minus P, right? So this is the condition. We need this to be empty, right? Okay. And so this is saying that Q set minus P is empty, right? And this tells us that Q is contained in P. Okay. So in particular, R P here, so this is S inverse of R for S as above, is a local ring with maximal ideal P. Okay, and so what this is saying is that all the other ideals, all the other prime ideals, so remember prime ideals correspond to varieties, right? They have to pass through P, right? P is the maximal ideal, or either that or it's the smallest point in there's only one closed point. There's only one maximal ideal in spec of R mod P. So spec of R mod P has only one bottom point.
So
Bottom point,
is
or-
it kind of like everything outside that circle kind of like divides into the stuff inside?
Exactly. That's what I was trying to. Exactly. That's exactly what's going on. That's what this picture. Where's the picture? That's what this picture is. So everything outside of here, right, goes into. But we don't really have divides because it, it doesn't quite, it's not a PID anymore, right? But yeah, that's the idea, right? All these other ideals are contained in the maximal ideal. But the thing is like the bigger the ideal gets, right, the more constraints that you impose. So the more equations have to be satisfied by points, right? And hence the smaller the object. So when you have big ideals, maximal ideals, those correspond to single points. The smaller the prime ideal gets, right, the bigger the subscheme, right? And so this is like all the subschemes that pass through a single point. That's what it can. That's the information that it contains. And all the drawings that we do, we're only drawing like all the closed points, but the collection of all these, the closed points are the maximal ideals. So those are the ones whose closure is itself, right? Maximal, yeah. So does that, yeah. So that's the correct idea.
That clears it up a lot for me at least. So like the bigger the ideal, the smaller like the restriction up until a maximal ideal, which is just the point. And
Exactly.
Then,
Exactly.
okay. Yeah.
Exactly. Yeah. The bigger the ideal, the smaller the thing. The more conditions that you have to impose. The fewer conditions, like so, if you're just cut out by one thing, right? Then then you're going to have more stuff involved. And that's where you get these slices. Yeah. All right, these were great questions. I'll stick around and answer more questions if you guys have any. But we're out of time for today. Yeah, so I'm just gonna. Should I leave the recording going if you guys have more questions, or?
I was just gonna ask to move it back. I couldn't copy down the last
Yeah.
sentence that you were writing.
Yeah. This should be on. You should be able to get access to this too.
Oh,
Right?
true. When is this program dying? You said
April.
April.
But we'll export them, right? And so that we have them all.
that would be great since I still can't access.
You still can't get it?
No, I can't. I have to fiddle with my browser, I guess, a bit.
Okay.
I might like I could probably just export it in the meantime and put it into the teams that the PhD teams that we're in, and then the class page. I can do that for up through 20 here. So,
Okay, that would be amazing.
yeah.
Thank you, Keith.
Yeah.
If you want to put like a little title to them too, that'd be great too.
I could do that
Like
to the best of my abilities.
Yeah, I'll go over them too.
Yeah. If anybody has alternate titles compared to the ones that I give them, please feel free to edit them.
Tyler, where did you want me to scroll to?
Oh no, I got the sentence. But when do you have I know you answer questions after class now, but we have another class pretty quick. So
Yeah. Tuesday.
when do you have office hours?
Tuesdays at noon.
Okay. Great.
You guys want me to move it? I can move it.
No, Tuesday and Thursday I have no class, so that's I'm up before noon, so that
Okay.
works for me.
All right.
Sometimes you don't get so lucky. 12:30 waking up is pretty nice sometimes when you don't have school.
Yeah.
Very true.
That's what I mean. I like working at night, so.
Take
Yeah.
it easy.
All right.
Thanks a lot.
All right. Thanks, Taylor.
Later.